Hello friends, welcome in a lecture of Dynamics of Machinery subject. Myself Mitesh Patel. I am assistant professor in a mechanical department at a Dr. Subhas Technical Campus, Junagadh. Today's our lecture topic is a dam-free vibration. In this lecture we discuss or solve the numericals of dam-free vibration. So before start this lecture, we summarize or revise some points. Okay, so let's start. First, what is the vibration? How to define it? So we all know that to and fro type motions or it repeat itself means the to and fro type periodic motion is called the vibration. Now, what is the free vibration? Okay. Now we discuss about that. To and fro type periodic motions is called the vibration. Now this vibration is called the free vibration, means the body is vibrate in free environment, no any resisting force to the vibration. So that type of vibration is called the free vibration. Let's take one example of that. It is a spring and mass system. Now we initially displace the mass and left that the spring and mass system is vibrate and no any resisting force are there. So this type of vibration is called the free vibration. Now what is the dam free vibration? How to define it? So let's take one example and define with that. Spring and mass and one extra element are added into this system. It's called the damper. Now we displace the body from the mean position, then body is vibrate, but here extra element is added. It's called the damper. And what's the damper is done? The damper is absorb the energy of vibration or resist the vibrating motion. So with respect to time, the vibration energy are decreased and the vibration amplitude at with respect to time decrease. So after some interval of time, body will be stopped. Okay. So here the one element is added due to the damper. The vibration is decay, and with respect to time is stop. Okay. The perfect practical one example is taken as our shock absorbers in automobile or bikes, in which the viscous damper are there. This damper is stop the vibration of spring inside the suspensions. Okay. Now we know that we very well understand the dam free vibration. Now dam free vibration have three types of dam vibration according to the value of zeta. Okay. If the value of zeta, first we discuss the what is the zeta. Zeta is a damping factor. It is the ratio of dam coefficient to critical dam coefficient. Okay. So zeta value is find out with this ratio dam coefficient to critical dam coefficient. Okay. Now according to value of zeta, we define the three types of dam vibration. First one, if the value of zeta is less than 1, then dam vibration is defined as a under dam vibration. Okay. If value of zeta is equal to 1, then dam vibration is defined as a critical dam vibration. Okay. If the value of zeta is greater than 1, then the dam vibration is defined as the over dam vibration. Okay. According to value of zeta, the dam vibration is defined in these three types. Okay. Over dam, under dam, and critical dam. Okay. Now let's start the solve the example. Okay. Take the first example. First, see the example which data is given. The spring mass dashpot system, okay, consists of spring stiffness 400 Newton per meter. Spring stiffness is defined by K. So K is given 400 Newton per meter. And how to find out the K? is a force per unit deflection to the spring. Okay. Now mass is given, mass of 4 kg. Okay. The mass is displaced 20 mm beyond the equilibrium positions. Okay. So spring mass despot system are initially displaced the mass from mean position 20 mm. So we can say that it is the displacement, initial displacement 20 mm. Okay. Find the equation of motion of mass, and if the damping coefficient of despot is a 160 Newton into second per meter and 80 Newton into second per meter. Here we have to find out the equation of motion, means the equation of displacement in the function of time. So at any moment of time we can find out the displacement of mass. So we have to find out the displacement equation in the function of time. So we put the value of time at any time. We can say that if we want to find the displacement of mass after a 10 second. So if we put the 10 second in this equation, then we find out the displacement of mass. That type of equation we have to find out in this example. Okay. In this example, the two damping coefficient is given. First one is a 160, another one is a 80. So first we have to decide what kind of damped vibration is there in case of 3. Okay, that is defined by the value of zeta. So first we have to find out the value of zeta, and we know that what is the zeta? Zeta value is find out with the ratio of damping coefficient to critical damp coefficient. Okay, so here damping coefficient value is given. So first damping coefficient is a 160, and we have to find out the critical damp coefficient. Now critical damp coefficient is find out with the 2m omega n. Okay, critical damp coefficient is find out with the 2m omega n. M is the mass and omega n is the natural circular frequency. Okay, or angular velocity, we can say that, natural angular velocity. And we know that in a spring mass system, natural circular frequency is find out with the under root k upon m. Here we have a spring stiffness and mass. So we find out the omega n. It is a 10 radian per second. Okay. So put the value of omega n in this equation, and finally we get the value of zeta 1 according to first damping coefficient value 160. What is the value of zeta? Is a 2. So we can define that the value of zeta is greater than 1. So which kind of damp vibration is there? For a first damping coefficient, over damp vibration is occurs for a first damp coefficient. Okay. Now for the other, here the damping coefficient is 80 and other value is same as per the first condition. Okay. And now we find the value of zeta is a 1. Okay. So here according to value of zeta, the vibration is a critical damp vibration for a second damp coefficient. Now we have find out the equation of displacement in a function of time. Now we earlier in the study in the theory, what is the displacement equation for the all three types of damp vibration. So directly we take the equation for the case of overdamp, displacement equation of overdamp vibration. So we write that x is equal to a e raised to in bracket minus zeta plus under root zeta square minus 1 bracket complete omega n into t. Okay, here is a omega n into t. Okay, plus b e raised to in bracket minus zeta minus under root zeta square minus 1 into omega n into t. Okay, now in this equation we put the all known value. So here zeta's values are put and omega n. Okay, so only t is remaining, and A and B is a arbitrary constant, so we have to find out the value of arbitrary constant. So only remaining is a t, and we find out the motion equation in the function of time. So anytime we can find out the displacement of mass. So what we have to do? First we simplify the equation and get this equation A as per shown in slide. Now for the find out the value of A and V arbitrary constants, first we must have two velocity. So this displacement is derived with the time and we get the velocity, we know that. So here we differentiate with the time, so e raised to x and x, okay. So here we get the equation of velocity, okay. Now we have to put or consider the initial boundary conditions. In this boundary condition we consider that at a value of initial, when the displacement is 0.02 meter, means the 20 mm which are given in example data. So at a time is a 0, not vibration is not a start. So at the initial, from that displacement vibration is start. So first condition is a t is equal to 0, x is equal to 0.02 meter. We have taken meter displacement, okay. And at that time the velocity is a 0 in the initial condition, because the vibration is just start, the velocity is a 0. So now this boundary conditions value are applied into the both equation of displacement and velocity. So we find out the value of arbitrary constant as shown in. Now put the value of boundary condition t is a 0, so e raised to t value is a 0. So only a plus b are there, okay, and x value is a 0.02 meter, okay. So from this boundary conditions value we get the equations 0.02 equal to a plus b from that equation, okay. Now put the value of the conditions in a velocity equation. So here t is equal to 0, so e raised to t is a 0, e raised to 0 is a 1. Now here the a1 and a2 or a or b, okay, only there and value is there. And now x dot is equal to 0. So here the value of a is find out in form of b from the equation of c, okay. So from that value of a is put and we can find out from this equation value of b. So now we have a value of a and b and value of zeta and value of omega. So put this first initial equation of displacement equation of over them, then only unknown element is a t time, okay. So according to time we have now find out the displacement of mass. If we have to find out the displacement after 20 seconds, 5 seconds, so put the value of second t in this equation. If I get the displacement after the 10 second or 5 second, what we have to find out, okay. So this is the final equation for a displacement at a particular time, okay. Now for the another case, zeta is equal to 1. So this is a case of critical damped conditions, and the equation of critical damped vibration displacement equation is this shown in slide. X is equal to, in bracket, a plus b into t, bracket complete, e raised to minus omega n into t. This is the displacement equation, and here a plus b is a arbitrary constant. So we have to find the value of arbitrary constant. The similar procedure are followed in the case of, in the ORDM case. So here we open the bracket and simplify the equation, and now we differentiating the equation with respect to time, so we get the equation of velocity. So here a is a constant, so e raised to x, e raised to 10 t is the differentiation is a e raised to 10 t, and further negative 10 t is differentiate is a minus 10. Okay, similarly here that b is a constant, and first time is t is equation, and second time e raised to minus 10 t differentiation, and we get the final equation. Now initial boundary conditions are also apply similar to the ODEM case, and value of initial conditions is same as per the given of example data. So here the put the value of time is equal to 0 and displacement is equal to 0.02. So put the value of both x and t in the displacement equation, and we get the value of a, because the here b into t, and if t is a 0, then the b value is 0. So we have to find out the value of a, 0.02. Okay. Now all the value, boundary conditions value is put in the velocity of equations, velocity equations. So velocity at the initial point t is equal to 0 is a 0. Now right side all the values are put, and b point is a 0. Now this element of equation is a 0. Here put the value of a, and here b. So we find out the value of b is a 0.2. Okay. Now put the all value in this first equation or displacement equation. Only the t is remaining. This is the final answer or final equation of motion. Okay. With respect to time, any point of time or any moment of time, we find out the displacement of mass in a critical damp and over damp. Okay. The example is complete. Okay. Now another example we take an over damp system shown in figure. The has a spring stiffness 14 kilonewton per meter. Okay. So we having a stiffness K is equal to 14 kilonewton per meter. Now it's converted into the Newton into meter. So it's multiplied by 10 raised to 3. Viscous damper having a damping coefficient 1400 Newton into second per meter. Okay. So damping coefficient C is given 1400 Newton into second per meter, and mass is a 8.6 kg. It's given. Okay. Now it is at rest in static equilibrium position when it receives an amplitude force acting to the right that impart an initial instantaneous velocity of 25 meter per second to the mass. Okay. The velocity is given, initial velocity is given, x dot is equal to 25 meter per second. Okay. And when it's in right side direction. Okay. First, determine the expression of the displacement x of the mass in terms of time t, where what will be the maximum displacement of the mass from the initial position, and third one is the what length of time will be required of the mass to attain the position of maximum displacement. Okay. So three values is find out. Okay. So first determine the expression of displacement x of the mass in terms of time. Okay. So first one is the natural frequency or damping factor. So first we consider the boundary conditions. Okay. What is the boundary condition? T is equal to 0 and x is equal to 0.01 meter. Okay. And the velocity is a minus 25 meter per second. Here the negative sign indicates the acceleration is reduced with respect to time. Okay. Now, according to boundary conditions, we find out the displacement equation, but we first have to decide the which case of damped vibration. So first we find out the zeta value, C upon Cc. Okay. So zeta equal to C upon Cc. So we having a damping coefficient, and we find out the critical damp coefficient. We know that how the critical damp coefficient is find out, 2m omega n. Okay. So zeta value is a 2.01. So this is a case of overdamp because zeta value is greater than 1. Now we know that the value of x or displacement equation for overdamp conditions or overdamp vibration, it is a x is equal to a into e raised to in bracket minus zeta plus under root zeta square minus 1 omega n into t plus b into e raised to in bracket minus zeta minus under root zeta square minus 1 bracket complete omega n into t. Okay. Now further in this equation put the value and further simplify the equation, and we get the final equation as shown in slide. X is equal to a into e raised to minus 10.74 t plus b into e raised to minus 151.27 into t. Now a and b is a arbitrary constant, so we have to find out the value of a and b according to the initial boundary conditions, and initial boundary condition is as per the given data in example. So here we consider the initial boundary conditions time at a initial time t0 at a starting moment of vibration. The distance is given is a 0.01 meter, means the 10 mm, and the displacement velocity is given 25 meter per second when start the vibration. So put the value of this in displacement equation, the value of x and this, and now we also know that how to find the velocity, differentiate the displacement with respect to time, then we get the velocity. So differentiate the displacement with respect to time, we get the velocity. X dot is defined by the dx by dt, so it's a velocity, dx dot is a velocity, and now a is a constant, so e raised to x differentiate is a e raised to x, and further x the differentiation is the with respect to time t is 1, and the only value is there. Now similarly e raised to x and x, further the x differentiation is a only value is there, t's differentiation is 1. Okay. Now put the value of velocity equation, t is equal to 0 and x dash is equal to 0. So put the value of this equation. Okay. So displacement is a 0 and time is a 0. So here displacement 0 and time 0. So e raised to 0, 1. So a plus b is equal to 0. Finally we get from the displacement equation. Okay. Now here the mistake is there. Here not a x dot, here is a x displacement. Now put the conditions value in velocity. So here we know that the velocity is a minus 25, and let's put value of velocity negative 25. Here the e raised to t value is a 0, so e raised to 0, 1. So value n a, value n b. Now from this equation and equation C and D solved by the both equation, we get the value of A and B. Okay. Now put the value of A and B in this equation and we get the value of, we get the relative or motion equation of displacement with respect to time. Okay. And we find the motion equations, okay, sorry, in this equation, and with respect to time, at any moment of time we find out the displacement, and this is called the motion equation of damped free vibration, or we can say that particularly over damped vibration. Now another solve the example. The machine weight 18 kg, okay, mass is given 18 kg in this example, is supported on a spring and dashpot. The total stiffness of spring is a 12 Newton per meter. So here K is a 12 Newton per mm and it's converted into the Newton per meter. Okay. So here 10 raised to multiply by 3 to convert the mm into meter. Now damping coefficient is given 0.2 Newton second per mm. So it's also converted into the meter per second. Okay. Here it's multiplied by 10 raised to minus 3. The system is initially at rest and the velocity of 100 mm per second is imparted to the mass. So initial velocity is a 120 mm per second. So it's also converted into the meter. So multiply by 10 raised to 3, 10 raised to minus 3. Okay. Determine the displacement and velocity of mass as a function of time and the displacement and velocity after 0.5 second. Okay. So two values we have to find out in this equation. Now the boundary condition is assumed according to data. So here displacement is 0 initially, but the velocity is given x dot 120 mm per second at a time of 0. Okay. So we know that now. For find out the motion equation, first we have to find out the damped free vibration, which kind of damped vibration is there in this case. So we have to first find out the value of zeta. Okay. So damping coefficient is given. So first we have to find out the critical damp coefficient. Critical damp coefficient value is a 2m omega n. M is given, but omega n we have to find out. So omega n is the natural circular frequency. We find out for the spring mass system under root km. So stiffness is given and mass is also given. So omega n value we find out 25.82 radian per second. Okay. And finally we get the value of zeta 0.2. So it's a less than 1. Zeta's value is less than 1. Then the damped vibration is a under damped vibration. Okay. Under damped vibration is there for the particular case or example case. Okay. Now we know that the displacement equation for the under damped case, okay, x is equal to capital X e raised to minus zeta omega into t and sine omega dt plus phi. Omega d is a circular frequency of, or we can say that damped circular frequency or angular velocity for a damped in another way. Okay. So this equation is a displacement equation for a under damped case. Okay. Now put the all known value in this equation and simplify the equation, and finally we get the equation A as shown in slide. X is equal to capital X e raised to minus 5.55t sine into sine in bracket 25.21216 into t plus 5. Here the two constants are there, 5 and capital X. So we have to find out the value of x and 5. Capital X is arbitrary constant. Okay, so we know that how to find out the arbitrary constant by applying the boundary conditions value. And first we have to find out the value of velocity equations from the displacement equation. So how do we find out? Differentiate the displacement with respect to time. So we get the velocity. X dot is a dx by dt. So x dot define the velocity. X dot is a velocity. And now here x is a constant, but e raised to minus 5.55t and sine differentiate with both. So rules of differentiation for a multiplication is applied, and here the first one is as remain. Sorry, here the sine is as it is, and the differentiation is done of e raised to x e raised to minus 55t, and in second time e raised to minus 55t as it is, and differentiation is done of sine factor. Okay, so here e raised to x differentiation is a e raised to x as it is, but the here x as a minus 5.55t, so its differentiation is minus 5.55 is a constant, and t's differentiation with t is a 1. Okay, so here, okay, and now in the another one, the sine differentiation is a cos theta sine theta to cos theta, but the theta is there. So first second theta's differentiation, 5 is a constant, so is a 0, its differentiation is 0. Here 2.5216 is a constant, and t differentiation with respect to t is a 1, so in multiply by 5.216. Okay, now boundary conditions is there, t is equal to 0, x is equal to 0. Now these conditions or these values of condition is applied to the displacement equation. So here t value is 0, so sine 5 x sine 5, and displacement is 0, so equation is a 0 is equal to x sine 5. But here the arbitrary constant value is a not 0, so therefore the value of sine phi is a 0, or phi is a 0. Okay, so now the value of 5 is 0, it's put the equation of displacement, then or velocity equations. So here the velocity equations, in that equation we have the value of, we take the value of 5 is a 0, and boundary conditions is a x dot velocity is given in initially, and t is a 0. Now all three values are put in the velocity equations, and now we get this time, because here e raised to t is a 0, so e raised to 0 e raised to 0 1. Okay, so here sine x sine 25 t, but the here sine 5 value is a 0, so sine 0, or we can say that here sine 5, and the minus 5.55. Okay, and here x it is e raised to 0 1, and cos 5, this term is 0, and 25.216. Here this value is come ahead in this hand. Okay. Now put the value of 5. Sin 0 is a 0, so this terms is 0. Now cos 0 is a 1, so this term is there. Okay, x into cos 0 1 into x into 1 into 25.216. Okay, and now we get the value of x. Okay, so now we have both values, 5 and capital X constant, so both constant value are there. So put in this equation and the only t is remaining, so put the after the value, putting the value of x and 5, then equation become as shown in slide. And this is the equation of motion with respect to time. So we can find out the motion of mass or body at a particular any moment of time or at a particular time. Okay, so in this example given that at a 0.5 second we have to find out the displacement and velocity. So in this equation we put the value of t is a 0.5 second, so we get the value of displacement. Okay, and for velocity is also find out. So here to put the value of capital X and 5 and t is a 0.5. Okay, so we get the value of displacement or velocity both. Okay, so I hope you very well understand the damped free vibrations and its numerical and how to we solve the numerical of damped free vibration. So you very well understand, and you can, I hope that you can easily solve the example. So first of all, in this example we find out the zeta and find the case of damped vibration, and according to that we put the equation or write the equation of according to case, which is a over damp, under damp or critical damp, and then find out the motion equation. Okay, so thank you for listening or watching our lecture. Okay, thank you.